Hi, my name is Prune and I'm going to present Warp consistency for unsupervised learning of dense correspondences. This is a joint work with Martin Danelljan, Fisher Yu, and Gool, and we're all from the Computer Vision Lab of ETH Zurich. In this work, we tackle a problem of dense correspondence estimation. From a pair of reference and query images, we want to find a match for every single pixel of the reference image. This is done by estimating the flow field relating the reference to the query. A common way to qualitatively assess the quality of the flow is to warp the query according to that flow, and the warp query should then resemble the reference. In this work, we're particularly interested in matching images with large appearance and viewpoint changes, so it can be images showing the same scene but taken from different views at different occasions or under different conditions like here, and that corresponds to the geometric matching task. And the second type of images we're interested in is semantic data. So here, the images depict different instances of the same object class, and the images therefore show drastic appearance changes and inter-class deformations. However, the major challenge of dense correspondences is how do we train the network? So supervised approaches require dense ground truth data, but it's virtually impossible to collect dense ground truth data for real image pairs. So one option is to manually annotate a couple of points, but this is very time-consuming and lacks accuracy. Another option is to obtain sparse ground truth as the byproducts of structure for motion techniques. However, sparse ground truth annotations do not provide complete supervision, especially in challenging areas such as homogeneous regions. Or finally, one can also resort to artificially rendered datasets. But because of the large domain gap between synthetic and real data, the methods trained on synthetic datasets might not generalize well to real data. So as a result, these strategies lack realism, accuracy, or scalability. In contrast, there are countless sources of unlabeled images and video data, which calls for the design of unsupervised learning approaches. For training a matching network unsupervised, we only require to have image pairs depicting the same scene or the same object. So now, let's look at common unsupervised approaches. The photometric or brightness consistency assumption has been widely used for unsupervised correspondence learning. The network is trained with the assumption that corresponding pixels should have the same intensity. This is the corresponding loss. So if you compute the flow field relating image pair I and j, and warp j towards I according to that flow, the intensity of the pixel should be the same. So for this pixel, it amounts to saying that this small patch is equal to this small patch. And you see that in this particular example, this is to some extent valid, but this is only because here the image pairs are consecutive images with very similar appearance and small motion. But in the more general case of geometric matching or semantic matching, where the images have large appearance variation between their frames, you see that the brightness constancy assumption doesn't hold. So while it uses real image pairs, the photometric consistency assumption cannot deal with large appearance and viewpoint changes. Another widely used unsupervised objective relies on the forward-backward consistency constraint. The predicted forward flow relating I to j should be equal to the reverse displacement of the backward flow between j and I. Translating this constraint into a loss leads to the forward-backward consistency objective. However, this objective is enforced by the trivial degenerate solution of always predicting zero flow. Therefore, the network is always biased towards predicting zero flow, even if combined with another loss. Another alternative which has been widely used for the geometric and semantic matches task is Warp-supervision, which is also referred as a type of self-supervised learning. Each training image pair is created from a base image by warping it according to a synthetically generated ground truth flow W. So here, the synthetic ground truth W serves as direct supervision through a regression loss. So as a result, the Warp-supervision objective provides a strong and direct signal which enables the network to learn to handle large appearance and viewpoint changes, but because the synthetically generated images cannot faithfully simulate real image pairs, Warp-supervision methods struggle to generalize to real image pairs. In summary, existing unsupervised approaches either rely on the photometric consistency assumption, which cannot handle large appearance and viewpoint changes, on the forward-backward consistency constraint, which has a degenerate solution, or on the Warp-supervision objective, which does not generalize well to real image pairs. In contrast, we introduce Warp consistency, an unsupervised learning objective for dense correspondence regression. Our loss leverages real image pairs without invoking the photometric consistency assumption. Unlike previous approaches, it is capable of handling large appearance and viewpoint changes and does not have any degenerate solutions. Now let's dive into the method. From an image pair I and J, we first construct an image triplet by varping I with a known flow field W to generate the new image I'. We now consider the full consistency graph containing all flow consistency constraints derived from the triplet of images. What is crucial here is that the transformation W is known. So the goal is to find consistency relations that translate to suitable learning objectives. And particularly, we wish to improve the network predictions between the real image pair I-J. The graph actually gives rise to many possible flow constraints. In the paper, we comprehensively analyze all constraints both theoretically and experimentally. But in this presentation, I will only focus on the most interesting constraints that can be translated into unsupervised matching objectives. So let's look at them. First, we observe that our consistency graph contains two of the unsupervised objectives I mentioned before. So from the pairwise constraints, we here retrieve the Warp-supervision objective and here the forward-backward consistency objective. As the main result from our analysis of the graph, we propose a new constraint which we call the W bypass. It is derived using all three images of the triplet. So the constraint enforces that the W flow should be equal to the composition of the flow between I' and J here and the flow between J and I here. But crucially, in our setting, the flow W is known. So we can therefore translate this constraint into this loss, and here we see that it provides supervision for the flow prediction between the real image pairs. Our final Warp consistency objective is the sum of the W bypass objective and the Warp-supervision objective. They are mutually beneficial because the Warp-supervision objective increases convergence speed, it also helps in driving the network towards higher accuracy, and because W is smooth by construction, it also acts as a smoothness constraint. On the other hand, through the W bypass loss, the network learns the realistic motion patterns and appearance changes between real image pairs, and it also increases the generalization capabilities of the network. We train three networks for two tasks by replacing the original network losses with our Warp consistency objective. For the geometric matching task, we train GlueNet and RenSac on megadepth images. For the semantic matching task, we train semantic GlueNet instead on semantic data from the PF Pascal dataset. So for all three networks, we obtain their Warp-C equivalent, trained with our Warp consistency objective. So first, we compare our Warp consistency objective to the existing unsupervised approaches I presented at the beginning. So we train GlueNet with different unsupervised losses on megadepth, and we here compare the corresponding network performances on the megadepth dataset. As metric, we use the percentage of correct key points for a threshold of 5. So let's look at the results. So first, the photometric census loss, which is popular in optical flow, here does not have sufficient invariance to appearance and viewpoint changes, and it thus leads to poor results on geometric matching datasets. The SSIM loss is more robust to the large appearance variations present in megadepth, leading to better results. Further combining it with the forward-backward consistency constraint leads to a small improvement. However, if we compare the photometric SSIM loss to our Warp consistency, we see that our Warp consistency approach achieves significantly superior PCK on megadepth. Then, we see that combining the Warp-supervision with the forward-backward loss leads to an improvement compared to only the Warp-supervision. But it is still significantly worse than our proposed loss, the Warp consistency. Now let's look at quantitative results on megadepth. So we evaluate in terms of PCK for distance thresholds of 1 and 5 pixels. So the first thing we see is that Warp-C GlueNet and Warp-C RenSac both achieve a substantial improvement compared to their respective baselines. And they also set a new state-of-the-art overall compared to previous unsupervised approaches. Here, we visually compare GlueNet and Warp-C GlueNet on an image pair of megadepth. So we see that our Warp consistency objective allows the network to handle the large and complex 3D motion present in real image pairs. We show an example of RenSac and Warp-C RenSac. So while the accuracy of the methods looks similar, we see that training with Warp consistency achieves a much better confidence mask. Here we evaluate the same networks trained on megadepth, but on the robot car datasets. And once again, we see that both Warp-C GlueNet and Warp-C RenSac substantially improve upon their baselines. And here it's also important to note that since all networks are trained on megadepth, our Warp consistency objectives improve the generalization capabilities of the networks. We next evaluate Warp-C semantic GlueNet on semantic data. So we look at the PCK on both the TSS and the PF Pascal datasets. So first comparing Warp-C semantic GlueNet to the baseline semantic GlueNet, we see that our unsupervised objective VOP consistency brings an incredible improvement compared to solely the Warp-supervision objective. Comparing to other unsupervised approaches, our Warp-C semantic LUNet also sets a new state-of-the-art on the TSS dataset and on the most restrictive thresholds on PF Pascal. It scores second after DCCNet for PCK01, but here it's important to note that DCCNet employs a much deeper feature backbone. So these are a couple of examples of baseline and Warp-C semantic LUNet applied to PF Pascal. Here we see that Warp-C semantic LUNet successfully adapts to intra-class shape variations and appearance variations where the baseline completely fails. The code is available, and thank you very much for your attention.